We saw in the last lecture that we could make two different pressure measurements. If the opening of a tube faced the flow, then the flow would go to zero. The flow velocity would go to zero at the entrance to that tube, and that would cause a very large increase in pressure, at least in the case that we studied, where the fluid pressure went up because of the Bernoulli effect. Dropping the velocity to zero caused a large increase in pressure. And if we measured the flow pressure with an opening that was perpendicular to the flow, so that the flow was not affected by the opening and essentially just passed right by the opening, then the pressure was measured at a different pressure, which is just what we call the static pressure. So the stagnation pressure is the one that is measured when you cause the fluid to stagnate, that is, to come to a zero velocity situation. And the static pressure is the measurement of pressure that we think of, as really the true pressure in the flow while the fluid is flowing. So this fluid is flowing right by, and so we're going to measure two pressures. So this illustrates a Pitot tube. So a Pitot tube is a device designed to essentially determine fluid velocity based on the difference between those two pressures. So the pressure, the gauge 1 here is going to measure stagnation pressure, so its entrance is facing directly into the flow. And a gauge 2, its opening is perpendicular to the flow, so the flow will pass right by it, maintaining its regular velocity. And so it will measure pressure that is not does not have an increase due to stagnating the fluid. So let's just do an example of this. If we see that gauge 1 is measuring 27,000 newtons per meter squared, and gauge 2 is measuring 22,000 newtons per meter squared. What is the velocity? So you have to know the density of air. So let's say this is air. Assume air flow with a density of 1.15 kilograms per meter cubed. So that would be your density measurement, and let's find V. What is velocity here? So this is an old technique that's still in use sometimes to measure fluid velocities. It makes use of the Bernoulli equation. So here comes the Bernoulli equation. P over rho plus V squared over 2 plus GZ is going to equal a constant. In this case, we're going to set that equal to flow situations 1 and 2. So we'll go ahead and set that up as P1 over rho plus V1 over 2 plus GZ1 is equal to P2 over rho plus V2 squared over 2 plus GZ2. Well, obviously from this picture, Z1 and Z2 are essentially the same. So those terms are just going to cancel out. So we're just left with this. And of course, we just said that the gauge 1 is measuring the stagnation pressure because the velocity at the entrance to 1 has to go to 0 because no fluid just can't keep flowing through this tube. So there's going to be no velocity at the inlet there. So that velocity 1 is also going to go to 0. So we have that P1 over rho is equal to P2 over rho plus V2 squared over 2. And that allows us to solve for V2. So V2, therefore, V2 squared is equal to 2 over rho times P1 minus P2. And that equation also has a name. That's called the Pitot formula. Pitot formula. So the Pitot formula allows you to calculate velocities based on the difference between the stagnation pressure and the static pressure. So this is the stagnation pressure, and this is the static pressure. And quite often these gauges don't even measure the true pressure. They simply measure the difference between these two pressures as their way of giving you more, the information that you need. You don't care what the absolute pressure is. You just care what the difference of these two pressures is. So, all right, so that's that. And now we're going to go ahead and just do the math here. V2 squared, therefore, equals 2 over 1.15 kilograms per meter cubed in this case. Obviously, that's the density of air, so that could change depending on your fluid and your situation. 27,000 newtons per meter squared minus 22,000 newtons per meter squared. Those were our pressures that we measure on the gauges, so you read those off the gauges. And if you do all that, you get V2 is equal to 93.3 meters per second. So that's the answer. The air is traveling at 93.3 meters per second. The question you could then have is, we know that Bernoulli is only good for Mach less than 0.3. Is this, sufficiently small to be less than Mach 0.3? You can look up the speed of sound in air, and you will find that this is in fact less than Mach 0.3. So this is a valid measurement for the situation. The challenge with the Pitot tube, however, are many. The biggest one is that this entrance has to be perfectly aligned with the flow. If it's tilted even a little bit, not perfectly aligned with the flow, you're going to get all kinds of viscosity effects. It's going to start swirling and spinning. The flow isn't really going to, it's not going to end. It's not going to really come to stagnation. It's going to have some kind of viscous effects, which is going to totally mess it up. And in addition, if velocity gets too high, of course, you'll have compressibility effects. As I said, the Mach number has to be below 0.3 for Bernoulli even to be valid. So you got to, be aware of that, though. So that doesn't often happen unless you're studying sort of aeronautics. And finally, you can't really use this technique for really, really low velocities because you just won't get enough pressure difference to really have a meaningful measurement.